In this topic, we will use Neo PID Tuner to estimate first order process models in DeltaV DCS platform. We will estimate the first order process models and then calculate the optimum PID and PI parameters for those process models in DeltaV. Our example first order model, in this example we have an heat exchanger, and we will warm up the temperature of the liquid. We will warm up the temperature of the liquid. The liquid is coming from here, and we have this steam from here. The valve is controlled. This valve is controlled by PID controller, and when we open the control valve, more steam will be fed to the exchanger and temperature will be raised. In order to estimate this process model, we need to put the control valve in in manual mode. We put the valve in manual mode, and we record the process reaction. The process reaction will be somehow like this, and based on the data provided, it's possible to estimate this first order process model and eventually calculate the optimum PID and PI parameters for this case. The first order process model is somehow the function test is somehow like this, and these are the values that are required for our data gathering step. This is the action. The blue curve is the action on control valve. The initial action on control valve is Y0, and this after the step change, the final action on control valve will be Y infinity. For process model, it's a bit different. This model should have the transportation delay. The transportation delay is possibly due to action on control valve, steam flow, and some thermal coefficients here in order to transfer the heat, and we this distance from the liquid from the exchanger, this transmitter, the distance of this transmitter from the exchanger may have some timing difference. When you apply the changes, you may need some seconds to find out the first changes. So this is the transportation delay. So if you have the step change, you need some time to see the changes on the process. This is the transportation delay. X0 is the initial temperature value, and X infinity is the final temperature value. If we have a noisy model, it's an acceptable noisy model. It's also possible for us with this level of noise to determine X0, TD, T infinity, and X infinity. So it's acceptable for us to gather this data and apply them to the application and get a somehow valid model and valid optimal parameters. But this is not if we apply the step and if we record this curve, it's not an ideal model for us. It's not a first order model. You can use the application, but possibly parameters, and the Laplace model is not accurate. The final parameter that we need is the T infinity. T infinity is our final stage. There are several mass explanation for T infinity. We reach to the T infinity if the slope of reaction curve is getting close to zero, or in some cases the difference between the points, if it's less than or equal to 1/100th of 1% of full scale, it's acceptable to consider as T infinity. There's another example here. In 1 second, we have the difference if it's less than or equal to 1/100th multiplied by 1% of full scale. If you are not happy with this mass, in order to determine T infinity, there is a simple visual clue. And if we consider the process reaction curve like some steps, and if we reach to the infinity phase, T infinity is the step with the widest constant step. The reaction curve is the slope of reaction curve is somehow constant, increasing here. We have the increasing here, and in this case we are getting close to a plateau, and the most the point that you can see that you have the least changes can be considered as the T infinity. You can use both these mathematical explanation or this visual clue. In this example, I try to use the visual clue because somehow mathematical complex issues is welcome in real industrial application. I have the application on my Android phone, and I have the DeltaV environment here, and I have this process history view for recording the trends here. Heater process is here, and it's a very simple program. Just I added the calculation box here. When we click on, when we make the tuning bit here true, the output, the PID output is in manual, and we apply 60 to the output, and we have a stopwatch here to count. And when we make it 0, the stopwatch will be stopped. So a stopwatch is crucial for our case. A stopwatch, as you can see, it's used widely. We need to measure all of these timing, TD, T infinity. So a stopwatch is necessary for us for measurement. If you don't want to use the stopwatch, you need to measure, the time and subtract the timing to find the time differences. But for easier handling this case, I use the stopwatch. In order to start the application, I'm in online mode, and I will make the tuning bit true, and we will record the PID is manual, and it will be the output will be 60, the manual value will be 60, and we will record the process. This is the process reaction. This is our PID output, and this is the stopwatch. We'll focus on the PID reaction, and that's the important parameter for us. I will pause the video and I will resume after we reach to the steady state in this test. So you can see that we are getting close to the final point, and it's somehow a fast process, and it's possible for you to restore the chart in order to have a very compact view, and it's possible, you know, to zoom if you want to have a better look here. And you can see that we will monitor all the process model here. You can see the steps here, and I think it's getting we are getting close to the T infinity, and I think if this final small step, let me zoom if it's possible. Here, I think here will be our infinity point. And about the infinity point, you can see the steps, the small steps here. This is the first step, and the longest step will be this. And I can conclude that we are getting to a very stable, near to zero a slope here. So this point will be our T infinity, and you can see that this step is constant and long enough to be considered to the our T infinity. Let me show you again. For T infinity, we had some mass here, complex criteria, but our visual clue, it's somehow approximate. You can see that when we reach to the city, we have a smaller step, and the first big constant step can be considered as the T infinity. And in this curve, we consider this point as T infinity, and the time, and the timer is showing 134. So we need to fill the data. The data is gathered, and we need to fill the data to the application. The first data is let me bring the application here. This is the Neo PID Tuner for Android application, Android devices. First, you need to check the license validity, and we select the first order model from manufacturer. We select Emerson DeltaV, and DeltaV is the platform. The starting point, x0 is 0, y0 is 0. We started from 0. The values can be seen here. PV and out is 0. And we need to check the TD. TD is the first non-zero value, 1.54. In 1.54, we have the first non-zero value in the transmitter, 1.54. Let me apply that here, 1.54. We go forward. We have the T infinity. T infinity, as I mentioned, the T infinity is, let me T infinity happened here, 134. So the biggest constant step here, 134, the biggest constant step here 134 points, 134. T infinity is 134. We go to the next. The final value is y infinity and x infinity. If we are in the final mode, you can see what's the final process value. The final process value is 72, and the final action valve is 60. So x infinity is 60 and y infinity is 72, and we check the validity. It's a perfect model. Gain 1.2, time delay 1.54, and time constant 26 seconds. And we check the reports. These are the optimal values here. I need to write them down, or I need to keep this this page. It's also possible to simulate the this process, these parameters with the estimated process model. Let me write down these parameters, and then I will try the simulation. Now it's possible. I wrote down all the optimal values here. It's also possible for me to simulate the dynamic process reaction to the different set of parameters: aggressive PID, conservative PID, aggressive PI, and conservative PI. I select the aggressive PID. It's also possible to simulate the reaction in the this application. First, I remove the manual mode, and I remove the reset state, and I change the set value, and we will see that the we have the full opening on the control valve, and the process is reaching to the set value, and the control valve is closing, and we are reaching to the set value. We will perform the same function test in the DeltaV. It's acceptable response. It's with a very slight overshoot. Our set point is 88, and we are getting 89. It's a very slight overshoot because it's aggressive parameter. I will move to the DeltaV, and I will apply the first. I will apply the PID parameters, and then I will apply PI parameters. So we need to go to DeltaV. We select the PID block. We go to mode. The mode is in manual, and I need to make the tuning back to 0, and I need to keep the output. I need to select the PID, and output should be 10%. I need to close the controller. Even I can make it 0. In the manual mode, I can change the gain. Gain should be changed to 2.68. This is the aggressive PID parameters, 2.68. We have the reset. The reset is 13.41, and you need to be in online mode for online changes. And we have rate. So reset is 13.41, and the rate is 1.35. So the PID parameters are applied here. We need to wait until reaching to the steady state, and after that all parameters are okay. We need to wait to reach to 0 and apply the step change for the so now we are getting close to 0. First I need to change the mode to automatic, because the parameters should be tested in automatic mode. And the set point, we should search for set point, and the set point we change it to 80. So we have a very big jump in this is the set value. The black curve is the action and control valve, and this is the process value. So we can see that the response is let me select the action and control valve. You can see the control valve is closing and the process value is reaching to the set point. We move the ruler here. We will have a very slight overshoot here, and that's okay. And you can see the response is very perfect. It's a very perfect response, very small overshoot, and we're getting close to the set value, and the error will be somehow 0. We are getting close to the set value here. The next step, let me change the disturbance. I will use the disturbance in case of PI parameters. I will apply. First I need to change the mode to manual. I will change the mode to manual. I want to be sure that the auto to manual transition is bumpless. Let me see if it's bumpless. Yes, it's bumpless. Now I can change the first I need to change the gain for PI, aggressive PI, or I can use the conservative PI. Conservative PI is 0.99, and we have the reset. Our reset is 31.14, and for PI we don't have the rate. Rate is 0. So we have PI parameters. Let me check them again. We have a gain, and all values are selected perfectly. We need to change the mode to automatic mode. Let me change the mode, and we apply a step change. Our set value is 80. I changed that to 90. And in this test, we will function test a very conservative PID parameters in DeltaV. The response should be slow, but as we expect, we avoid the overshoot here in this case. We are getting close to the set value. Let me put the cursor here. We're getting close to 90 here. It's a typical PI response, and we're getting close. It's very slow. It's also possible for us to use the aggressive PI for faster response. You can see that 88, 90, we are getting close, and This can be, so it's an acceptable response. We are getting to the set value here, and now it's possible for us to check the disturbance. In normal condition, if for a startup and for warm up, I suggest to use PID, aggressive PID, for to feel from 0 to reach to a high set value. I suggest to use aggressive PID, but for normal operation, conservative PID is okay. Conservative PID is okay for small step changes in set value and for controlling the disturbance. Now I will apply 5% of disturbance in the process and see what will happen here. We have a very slight change in the process, and the PID controller will what can I say, compensate that very quickly. If I make it a bigger disturbance, like 10 or 15, let's see what may happen here. It was a very a bigger disturbance. You can see that the temperature is increasing and the valve is closing. The conservative PI parameters should be able to compensate the process and to return to the set value. This is the second responsibility of PID controller. The first responsibility is to regulate the process in order to reach to the new set values. This part it's okay. You can see that we reached to the set value with a very slight overshoot. The next responsibility is rejecting or compensating the process disturbance. We had the process disturbance, we had a huge process disturbance here, and the PID controller is able to compensate that. And there are many other ways in order to compensate that quickly, like the feed-forward application that is out of the scope of the this example. So in summary, we have used the new PID tuner for DeltaV, and I'm very happy with the result. This is for first order process model, and the next step will be more complex process models like second order or higher order process models. Thank you for watching. If you want more information about this application, I will provide it in the description of this topic.